The first speaker is Martin Bridson. Last week we celebrated his birthday conference. He's a bit tired, but still he will give us a talk about free-by-cyclic groups for finite rigidity and deficiency.
Thank you, Alex. I'm glad Alex gave you my excuse because I was going to make it anyway. I really enjoyed myself last week. That might show in this lecture. So, also, I didn't realize the 50-minute thing, but that's okay. After 50 minutes, we'll see what happens. So I'm going to, this conference on non-positively curved spaces, I'm going to talk about a specific class of non-positively curved spaces. So X will be a finite metric graph. And phi will be an isometry of finite order. And the non-positively curved spaces I'm going to talk about are the mapping tori of these things. Okay, so the mapping torus, as you all know, just take space, cross it with the interval, and then stick one end to the other using the isometry. Okay, that's the class of spaces I'm going to be talking about this morning. Now, what I'm really talking about are the groups that go with those, right? So there's a realization theorem, sometimes called color realization, but it was proved independently by a number of people who I ought to have looked up, Gerasimov maybe, Color and somebody else. And so what groups do we get here? So the following conditions are equivalent for finite presented groups gamma. So it might be the fundamental group of something in this class, some x and phi, or it's a finitely generated free-by-cyclic group. This you should think of as the holonomy map coming from the bundle, the mapping torus of some phi of finite order. So that's really the realization theorem. Now, the realization theorem is that 2 implies 1. Right? That whenever you have an element of finite order in the outer automorphism group of free group rank n, you can actually find a finite metric graph of rank n so that outer automorphism is realized as an isometry. That direction is the realization theorem. And the third thing, which isn't hard, but it requires a little bit of thought is that it's exactly the free-by-cyclic groups that have non-trivial syntax. So those are 3 equivalent ways of defining this class of groups, and that's the class of groups I want to talk about. An important remark, which I'm really going to emphasize, perhaps overemphasize today, the fibering, which you might take to mean the algebraic fibering or the geometric fibering, is not unique. There is no claim that there's a unique way of fibering one of these groups or one of these spaces, or even one of those spaces. Perhaps a little more surprising with the spaces. These up to homeomorphism, it's not a unique fibering. Okay, right. Now, so that's the start. Now, the second word in the title is deficiency. And I'm hardly going to talk about deficiency at all, okay, except right at the end. Okay, so the talk will seem to be about something entirely different, and then right at the end I'll say something about deficiency. Okay, so let me remind you what deficiency is. So if you've got a finite presentation, so suppose that you've got so P is a presentation, finite presentation of a group. Then the deficiency of the presentation This is one of those things that there's a minus sign, that half the world uses one convention, half the world uses the other. Except that's not quite true. 99% of the world uses one convention and 1% uses the other. But Carl Grunberg was a wonderful man a long time ago, poisoned me with the wrong convention. But I'm now trying to correct this. And so so I'm going to do the now almost universal one. That the deficiency of the presentation is the number of generators minus the number of relations, and not the other way around. And then the deficiency of the group is I have to take a soup, right? A soup over the presentations, the deficiency of P, where P is the presentation of gamma. Okay. Right, this is if you never thought about this, it's a very easily defined invariant. It's an extremely hard thing to work out. Right? It's really a very hard invariant. There's lots of hard open problems about it. And rather than just waffle about that, let me give you an example. Here's a group which myself and Michael Tweedale, studied a family of groups that included this one. So the relations are A squared is the identity, B cubed is the identity, A commutes with its conjugate by T, and B commutes with its conjugate by T. Okay, that's 3 generators, 3 relations. Sorry, 4 relations. So that means that the deficiency of this group, it's not hard to see, the deficiency of this group is either, well, it looks like it's -1. Right? The betting is you can't do better than that number of relations. But it could be 0. Right? It could be that there's a balanced presentation. A presentation lists the same numbers of generators relations. That's your homework. Right? If the deficiency is -1, which means you can't do better than this, right? You can't get a balanced presentation, then you will have found the counterexample. It's not the counterexample isn't this group. We can build a counterexample out of this group to Wall's D2 problem. You'll have proved that there exists a group that has a 2-dimensional classifying space. It also has a compact 3-dimensional classifying space, but it doesn't have a compact 2-dimensional classifying space. So that's a hard problem. Right? That's really a hard, decades-old problem. So that gives you some indication that even in explicit examples, deficiencies are really hard invariant. It's very hard to work out what's going on. Oh, I haven't left myself enough room. Let me put it here. So, oh no, let me not put it there. Now, here's an old problem. I haven't checked the exact history of this. I think maybe Giles did. Can one simultaneously optimize the deficiency of the group and the number of generators of the group, and the number of generators? In other words, does there exist a presentation of deficiency with the number of generators in the presentation equal to the rank of the group, the minimum number of generators of the group? Okay. Old problem. Now, it's an old problem that I poison my students with periodically. And I had it on good authority. This was an open problem. And so I worked quite hard on this. And there's a theorem. And the theorem is no. If I've said it right. In other words, you can't always minimize the, optimize the deficiency and minimize the number of generators at the same time. Okay? And I'm going to explain to you right at the end why that theorem. But having proved that theorem, I then realized the answer had been implicit in the literature for decades. Okay, so you can't optimize sufficiency and rank the groups at the same time, and I'll show you an explicit example right at the end. I think it's open for finite groups. Okay, so I'll come back to that at the end. But what I'm really going to talk about is free-by-cyclic groups and then profinite rigidity. But before I get on to profinite rigidity, I want to talk about this lack of uniqueness. Where am I going to put my examples? So do people mind if I know this is bad practice, I'm just going to wipe out what I just wrote there, okay? I'm just going to, I want to use this board and leave it here, and I'm going to need my colored chalks. Sorry, I'm going to write this out, okay? Everyone got the problem? It's not a hard problem to remember. Right. But I want to come and talk about this difficulty. So these are going to be examples to show the difficulty of recognizing if some group in our class is isomorphic to some other group in our class. So this is about the non-uniqueness of phi prime. Okay? We might take some votes or not. Ever since Brexit, I'm much less keen on votes. But we'll see. We might vote on some of these. So here are some examples of groups. And your homework, if you don't want to listen to this lecture, you can do this. Decide which of these groups are the same and which of these groups are different. Okay? Everyone got the homework? So the first one is, I pick out a special generator, and I leave the rest in a rows. Oh dear. That's why you've got the color chart. Right, so there's a special generator, and then there's everybody else, A1, A2, round to AN. And here, the automorphism is I fix A to 0, and then everybody else has just moved around cyclically. Right, so AI goes to AI plus 1, mod N. Okay, there's one group. Here's another kind of similar group. So instead of putting them all loops at a point, this time A0 is the loop that goes around the middle, and I just do the obvious thing of one click. Okay, we've got that. So here, if you work it out, it's the loop in the middle is going to itself. There's no base point fixed this time, so you have to pick some maximal trees and things. So AI, so again, I'll just label them the obvious way, going around. So AI goes to AI plus 1, at least for I equals 1 up to n minus 1. And then the last one, AN will go to A1 just as a loop, but if you have to pick a tree and there's some base point problems, so what you actually find is you're conjugating by A0. Okay. All right, so we'll give these names. Let's call this phi 1 and phi 2. They both look like F plus 1. There's phi 1, there's phi 2. Are they isomorphic? Should we have a vote? Who thinks they're isomorphic? Who thinks they're not isomorphic? Okay. How are you going to prove that? Well, if you look at the action on homology, they're both doing the obvious thing. They're shifting those along and then putting the last one up there. Right? So you're not going to tell by acting on homology. And actually, if you look at terms lower central C's, that's not going to help much either. But are they? They're not isomorphic. Right? But it's not entirely obvious. Okay, here's some more interesting ones. How about if I take that to be my graph, and the obvious just rotation of order 3, okay? And then I take 5, and I take that of order, that click of the rotation of order 5, okay? But I'll also take alpha 5 squared there, okay? Now, you might ask yourself, are those different? So there's a free group of rank 6 extended by an action of z, and there's another one that has index 2 in that, but are they isomorphic or not? Think about that. Okay, how about this one? So taking an odd prime, I'll take 6. And now I'm going to do two things. So again, I'll take alpha 6, just rotate. But let me also take alpha 6 prime, which is rotate and flip the loop. Okay, so you rotate it and you flip all the loops. Everyone got that isometry? Yeah. Are those the same? Are they the same as their square or their fifth power or something? Okay. And here's one more. Just take the rotation of order 6 there. Is that the same or different to all the others on the list? Okay. So I'm not asking are the automorphisms the same, right? I'm asking are the mapping tori the same. Okay. Oh dear, I've run out of room. I'm going to have to put examples somewhere else, so I'll put them over here. Now this next example is really about odd co-prime numbers, but that's beyond, so the odd co-prime numbers are 5 and 3. Okay, but there's nothing special about 5 or 3 is what I want to say. Okay, so draw your two concentric M-gons, and then connect it with a little cage with our bars in it. Okay, so this is my graph, the 5 and 3 picture. Okay, and then alpha is going to be sort of the one that captures the most spirit here. So alpha is rotate. Well, I like to think of it as rotate and click. So you rotate just one fifth of a turn, right? And then you permute these cyclically. Is everyone happy with what that is? Okay. And now, so that's one group, right? So this now you might, I want to ask, oh God, I have to work out what the rank is. What's the rank of that? Quickly. I think, whatever it is, I think it's 11, is it? I think it's 11. It might not be 11. So there's that. And then what happens if I do alpha squared? Are they the same or different? Okay. Now let me give you a clue there. Here's a proposition that alpha is conjugate to alpha to the j in out F11. I hope it is 11. If and only if j is congruent to what? Plus or minus 1 mod m, which is 5 in this case. Okay? So you can see there's some arithmetics thing that's coming in here. And what's the point about being conjugate? Well, the point about being conjugate is there'll be a fiber preserving isomorphism from this one to this one, if and only if they're conjugate. And 2 is not congruent to plus or minus 1 mod 5, so there is not a fiber preserving isomorphism from there to there. Okay, so the mapping tori, you can't send one to the other in an obvious way. And then my final, oh no, it's not my final example. Oh God. These bigger boards here. Let me put one, let me look like I'm going to redraw that, that graph up there. But let me draw the pentagon differently. Now, how am I going to draw it? Carefully here. I'm going to draw it like that. Now, is this me just drawing the same object in a slightly different way or not? All right, so now, so what's beta? So beta is rotate and click in the same way, right? Just rotate this. Had I drawn it better, so I've forgotten I call it chalks. I just rotate by a fifth, and I permute each of these nests of cages, 3 edges by 1 click. Okay? Looks very similar, except it's a different pentagon. Okay? So how about is alpha the same as beta? Okay. And I could also ask, again, is are beta and beta squared, do they give different groups or not? And this time, let me tell you why I like this example. This is more than a proposition, it's a little theorem really. This requires quite a bit of theory to try. Sorry, this requires quite a bit of theory. I only know how to prove this in quite an indirect way that uses Krustig and Voigtman's theory of equivariant outer space, okay? And that is that alpha and beta, so those are both subgroups of order 15, cyclic groups of order 15 out of F11. Those are not conjugate. In out of F11.
Even up to inverses.
Sorry?
Up to inverses.
Yeah, yeah. They're just not. Right? They intersect trivially, these guys. Yeah, thank you. Okay. Right. Okay.
But they're not conjugating out at 11 does not mean they are not isomorphic.
No, it doesn't mean they're not isomorphic. What it does mean, so here, so this is already saying there's no fiber preserving isomorphism here, right? But that's kind of a trick just with the cyclic subgroups are the same. Now often students often make the mistake of thinking a semi-direct product is determined by the image of the map of the action of this on this, and it's not, right? And that, it's not. And so here they have, those actually have the same image, those Z's, the same cyclic subgroup, but you've got a different choice of generator. Here, these groups, they're really different actions in the sense of the image of the Z is different in both cases. And so again, there can't be a fiber preserving isomorphism, but that doesn't mean there isn't an isomorphism. Oh, sorry, one more example. Which again hints at some arithmetic going on. Right. This is the first line of my notes that we're on. Let me now let me take 3 primes, so let's say 2, 3, and 5. Okay, so this has an obvious kind of, again, isometry that picks everything up. So you take the isometry that flips these and cycles those through 3 and cycles those through 5, so that'll have order 30, right? Everyone happy what I mean by that? So it's a maximal isometry of that. So again, I didn't check. 1 plus 2 is 3 plus 4, I think that's 7. But what happens if I change the order of the primes? Suppose I do 2, 5, 3. So, are those isomorphic? No, I didn't do much. Right? I just swap the order of those cages. Are those the same group or not? Okay, we'll come back to that one. So, but I hope, time allowing, that we'll run through this list later and decide. Okay. Well, this is supposed to make you think that there are reasons I've chosen these examples. They illustrate different phenomena, but it's supposed to make you realize that deciding if free-by-cyclic groups are the same, even with finite order holonomial, it can be a tricky business. Okay. Right. Now back towards the results. Okay. So now I want to. Oh, sorry. Before I do that. Let me remind you of the dictionary between free-by-cyclic groups, depending on which side of the Atlantic you're on, and 5 to 3 manifolds. Okay, so it's kind of the same deal, right? You've got a mapping tori of surface automorphisms versus mapping tori of graphs, except here, if the holonomial is finite order and out of Fn, you can do isometries, otherwise you have to do homotopy equivalences, right? Whereas in surface world, homotopy equivalences are all isotopic to homeomorphisms, so you can actually get 3 manifolds. But if you think of these mapping tori of homeotopy equivalences, then this is really a direct translation, right? And if the surface, of course, has that, so here the groups are that, if the surface has boundary, then they will be free-by-cyclic groups, but a very special type of free-by-cyclic group arises like that. And how does this dictionary sort of play out? So here we have the train track technology of Vespina, Fein, and Handel, and here we have the Nielsen-Thurston classification of automorphisms, and it's not perfect. So here, so the pseudo-Anosov, which give you hyperbolic geometry, and where you get your hyperbolic groups, that you'd like to say there's something exactly analogous on this side, but it's slightly tricky in that the sort of full pseudo-Anosov behavior is something called fully irreducible automorphisms. But you also, you can do things that you can't do in surface world, right? You can have a free product decomposition and something hyperbolic there and something hyperbolic there, but it's obviously decomposable, right? And that sort of thing can't happen in surface world. So within the hyperbolic geometry, that now has to be hyperbolic in the sense of Gromov, you can also just have a toroidal, which just literally means that phi has no periodic conjugacy classes. Right. It doesn't leave any conjugacy class invariants or even have periodic orbits among the conjugacy classes. Okay, so that's the hyperbolic world. And then there's the polynomially growing, which I'm not going to talk about at all today. And again, these correspond to multi-twists over here. Okay, but multi-twists only have linear growth, and there's nothing else. We're not going to talk about that. Okay, but then what is the same is the periodic. Okay, so that's perfectly got periodic automorphisms on both sides, and then this is Seifert fiber geometry. In particular, it's closed case. It's H2 cross R geometry. Okay. And then you sort of have the exceptional low genus stuff. And again, there's two, well, on this side it's fairly clear, just rank 2 is special. Well, let's just ignore rank 1. And why is rank 2 special? Well, because the outer automorphism group of F2, the natural map to GL2Z is an isomorphism. That's the special thing that counts for why everything's different in rank 2. And that over here corresponds to genus 1. So then you get Sol and nil geometries as well as Euclidean. Well, Euclidean, no, Euclidean also goes up here. Well, but that's not quite true. So this time, just as we had 2 bullet points here corresponding to 1, in the exceptional case, you have 2 bullet points on this side. You also have punctured tori. Okay, so you also have punctured tori. In fact, every automorphism of outer automorphism of F2 can be realized as a diffeomorphism of a punctured torus. And so this brings back in hyperbolic geometry as well as the others. Okay, so that's our dictionary. And I want to be guided by that in what I want to do next. So I want to talk about profinite rigidity. Okay. Now, I'm not going to give a background lecture. I hope you've all heard me or Alan or somebody give a a survey, but let me just remind you what the key idea is. The key idea is you're interested in the extent to which a finite generated or finite presented group, which you might as well assume is residually finite if you're going to get anywhere. So take a finite presented, residually finite group. You want to know to what extent can I understand the group just by looking at its finite quotients. Right? Now the most extreme thing is profinite rigidity, where you can just recover the group completely from its finite quotients. So the way of saying that is that, so to remind you, so group gamma, it's finite generated, residually finite, is profinitely rigid if you take a group you find in the gutter that you happen to recognize as being finitely generated or residually finite, if it has the same set of finite quotients, which by bits of theory is the same as saying that profinite completions are the same. So if you don't know what profinite completion is, read this sentence as saying the set of finite quotients of lambda is the same as the set of finite quotients of gamma. Okay? So I'll say with that more precisely in a minute. But anyway, when they're equivalent in this weaker sense, it's a rigidity theorem. So it should say equivalent in a weaker sense implies equivalent in a stronger sense. So you can recognize the group just from its finite quotients. And so if you like, you can think of this as the set of finite images of lambda. But more precisely, lambda hat is the inverse image of, you take all of the finite images, right? So you take all of the finite images of your group. They form an obvious directed system, because if you take a finite image and you map that onto another finite image, you've got arrows, okay, so it's a directed system. Take the inverse limit of that. These are nice compact topological groups, finite groups. Take the inverse limit of a system of compact topological groups. You've got a compact topological group, and that's what you're really gaining here. This is a compact topological group, okay? And so that gives you extra structure to play with, but nevertheless, there are theorems that say that the set of two groups have the same set of finite images if and only if these compact topological groups are isomorphic. Okay? One direction is easy, one direction is hard. One direction is very hard, because I've sort of assumed the Siegel-Nickloff theorem, which relies on the classification of finite simple groups. Hey, everybody happy? I say you don't have to know a lot about profinite groups for this talk. It's in the background, it will be used, but really, something's profinitely rigid if it's completely determined by its set of finite quotients. Right, so we want to do this. We're interested in the extent to which, okay, so I'm going to put this here, open question. Are free-by-cyclic groups all profinitely rigid? Now, there's various ways in which you might interpret that question. From what I've said, the most extreme version, the most optimistic version, was take any group like that, then you could distinguish it from any other finitely generated residually finite group by looking at its finite quotients. I don't think I'm that optimistic, okay? But we're miles from knowing this. So Andre Heiken here has lovely results towards recognizing whether the free group itself is profinitely rigid, but that's a big open question still. Okay? We don't know if the free group is profinitely rigid, and somehow, once you prove that, this is still going to be a hard problem. Okay? So we don't know if a group you find in the gutter that's profinitely isomorphic to a free-by-cyclic group is going to be free-by-cyclic. Put that aside, let's just stick to groups in the class. Right? If you just think only of the class of free-by-cyclic groups, can you distinguish one of those from another just by their finite quotients? Right? That's the context for this talk, right? That problem. Can you distinguish amongst free-by-cyclic groups just by their finite quotients? And to motivate what we might expect, we're going to look on this side. Okay? We're going to look on this side of fibered 3 manifolds, see what we know there, and then try and push it across to make guesses, which we'll then have to prove on the free-by-cyclic side. So let me say what we do know on the right here. So on the right, let's start at the top with H3. There do exist, so that this is myself, Bemis, McReynolds, and Spittler. There do exist lattices both uniform and non-uniform, torsion-free and with torsion, that are profinitely rigid. Okay, so there are hyperbolic 3 manifolds that are profinitely rigid in the absolute sense of that definition. The conjecture, Alan and I might be the only ones who believe this conjecture, but nevertheless, I know Henry back there is a skeptic. All hyperbolic 3 manifold groups are profinitely rigid. Okay, that's just a conjecture. Now, but there is a lovely theorem. That's a theorem, I guess. This is by Yi Liu. That so you should think of this as a finite genus theorem. Only finitely many hyperbolic 3 manifold groups can have the same profinite completion. That is can have. Okay. So within the class of hyperbolic 3 manifolds, you take your favorite one and you ask which others have the same set of finite quotients, only finitely many.
And are all of those virtually isomorphic?
That is a good question. Yeah, we don't know. We don't even know if they all have the same volume. You'd think the proof might go by proving that volume is a profinite invariant, and that gives you that theorem. The way the proof actually goes is, so we know from Hegel that the manifold will have a fibered, a finite sheet of covers that's fibered, which gets us into this world. Then Andre proved that fibering is a profinite invariant. So the mystery guy, the mystery guy will have a cover of the same index, which is also fibered. So now you only have to decide profinite isomorphism among fibered guys, which is our world today. Okay? Then what Liu proves is that the dilatation of the pseudo-anosive monodromy is an invariant. So it's not quite volume, but the dilatation of the pseudo-anosive monodromy is an invariant, and there's only finitely many mapping classes that can have the same dilatation. So that's the way the proof goes. So they are similar in some sense, right? We don't have virtual isomorphism or same volume. Oh yes, right. So I'm supposed to tell you what happens on the left. So on the left, you hope for the same sort of finite genus theorem in the hyperbolic setting. We don't know that yet, but there is a very nice theorem by Sam Hughes and Monika Kudlinska that says at least some. So they prove more than this, but in particular, what they prove is if you've got two free-by-cyclic groups and those are what are fully irreducible automorphisms, names. Let me call that gamma 1, gamma 2. And gamma 1, same as gamma 2. And I need one more hypothesis, so I need the B1, the first Betti number, which is a profinite invariance. So these guys have first Betti number 1, which is sort of telling you the vibration is unique, right? Which all our examples are going to tell us is a big reduction. Then you do get profinite. So that's the step. Oh, sorry. That's not been proved, is it? It's finite genus, isn't it? Yeah. Yeah. Sorry. Yeah. Sorry. You take a fully irreducible guy with B1 equal 1. Then there exists only finitely many, the same as the use theorem. There exists only finitely many other guys of the isomorphism with the same profinite completion. Okay, so it's the finite genus theorem in the hyperbolic case, which is what you would like, but it's not quite the full hyperbolic case yet because it's fully irreducible rather than toroidal, and there's this thing that makes the five-ring unique. Okay, but what I want to talk about, which I haven't left myself enough time to talk about properly, is this case, the periodic case. I'm supposed to change color. It says in my notes. So I want to talk about the periodic case. And here, the news in the three-manifold setting is negative. There's a surprising paper. It's not a hard paper, but it's really a surprising result, I think, of John Hempel. He sadly died before it's published, but you can find it on the archive. And this is to do with you taking hyperbolic surfaces and you're taking periodic holonomial. Okay? So these are going to be manifolds with H2 cross R geometry. Okay? You have H2 in the fiber direction and then product in the holonomial direction. I'm not going to give the exact statements, but sort of generically, if M is the order of the phi in the mapping class group of the surface, and J is co-prime to M, then the fundamental group of the mapping torus the fundamental group of the mapping torus of phi won't be the same as the fundamental group of the mapping torus of the power of phi, of that finite sheeted cover. Okay. Now, how do you prove they're not the same? You use the Seifert fibered structure, right? That you use the Seifert data and what we know about three-manifold groups being determined by the Seifert data, by the base orthofold. But the profinite completions of these groups will be the same. Okay? So that's a lack of profinite rigidity. Okay? Now, how do you prove this? Well, that bit isn't hard if you know an old theorem of Gilbert-Baumslag. Let me just put it here. It's an old theorem of Baumslag, which just uses an even older result about finite groups called the Remak-Krull-Schmidt theorem that says if G1 cross Z is isomorphic to G2 cross Z, so if they're stably isomorphic after one step, then that implies that they have the same. I've been a bit casual about the hypotheses there. That's basically what it says. Okay? And if you think about it, here, with these groups, you've got the surface group semi-direct product Z. If you cross with Z, then you can sort of do a base change in the Z squared that you now have on the right. And so it's easy, actually, in this case, to see that those groups become the same after you cross them with Z. Okay, so that's stabilization technique. Nevertheless, this is the theorem that's of interest to us. Okay, you take these covers, and that should remind you of all this messing about I was doing over here. Okay, about taking co-prime powers of things and seeing what it does to the isomorphism class of the group. And in a minute, I'll talk about the profinite isomorphism class of the group. So I better state a theorem.
So example say is for closed surface or for any?
That's a good question. He does it for closed surfaces and for surfaces with boundary. What I stated is the closed case. Okay, that's I've been a bit casual. That picture's supposed to be closed surface. Okay. The theorem works in the case with boundary, but instead of talking about arbitrary isomorphism here, you talk about isomorphism that preserve the peripheral structure. Right? So you say there aren't isomorphisms that preserve the peripheral structure, but that's about to become important. Because of the following theorem. Okay, so this is the main thing I want to talk about. So this is something I proved my student Pavel Pivek. That's about to appear, I think. Which is this. So so let's say let gamma 1 be a free-by-cyclic group. Gamma 2 be a free-by-cyclic group, not necessarily of the same rank, the same genus here. But I want to stick to the sort of H2 cross R case. I want to stick to the periodic case. So phi 1 and phi 2, finite order. In the anti-automorphism groups. Okay, so two free-by-cyclic groups with center is a shorter way of saying it. So in this case, in contrast to what happens in the three-manifold case, if they got the same profinite completion, they are the same. Okay. So here we get profinite rigidity. Unlike in the three-manifold case, in the free-by-cyclic case, you do get profinite rigidity with periodic holonomy. Everyone? Yep.
What does it imply in terms of M and N in this case?
Good question. Yeah, what does it imply in terms of M and N? Not much. So let me actually, maybe this is a moment to go back to my examples. These groups are different. That one and that one. This one is actually F2 cross C in disguise. I'll leave you to think about that. And it's because the Galois group here the automorphism is the generator of the Galois group of a covering of that to the rows. Okay? And so the point is that the cyclic group is acting freely. Not just the generator is acting freely, but the whole cyclic group is acting freely. And so that's the covering map, and that is F2 cross C in disguise. I kept lying awake at night convincing myself of things like that and then unconvincing myself repeatedly, right? But if you do it with enough coffee, you'll be sure that's true, right? That one isn't, right? That one, it's not F2 cross C. It's the fact that it has a fixed point really matters here. That one doesn't have a fixed point, that one does. Okay, those groups are different. Down here, what's that one? Got any takers? Yeah, that's also F2 cross C in disguise. For the same reason, you just that cyclic group of order 3 acts freely. You take the quotient, get F2. Whenever you have a Galois group, whenever you have the cyclic group acting freely, you'll always get the quotient cross C. It's actually a very interesting exercise to take the mapping tools to this one and try and draw different fibering so that you can see it's F2 cross C. How about that one? Oh, you're getting the hang of this, right? That's F2 cross C. But then that argument applies equally to that one or that one. They both generate the Galois group. okay, of the covering of F2. So those are actually both the same group. But actually, those two automorphisms those actually are conjugate in F6, if you get out of F6. Right, now here I did something different, right? I could rotate, or I could rotate and flip them all. But those Z mod 6s are acting freely. So the same argument which I've mumbled a few times about that it's just a Galois action means that all of these are also just F2 cross Z. Okay. And likewise that one. So those are actually all F2 cross Z's in disguise. Which brings us back to this question of, in this profinite rigidity theorem, are we going to have the same rank of the free group? Well, no, we're not, right? Because up to isomorphism, you can't spot what the rank of the free group is, right? That's perfectly good F4 by Z group. It just happens to also be F2 by Z, etc. Okay? So the rank is something you can't spot, which tells you that the obvious way you're going to try and prove this theorem is not going to work, right? The first thing you try and do is, well, the first rigidity is you'll try and figure out the rank of n by looking at the profinite completion. That can't work, right? So you can't treat these groups as fiber groups when you try to prove this rigidity theorem. Those groups up there, these are interesting examples. There's no fiber-wise isomorphism from that one to that one, but they are isomorphic. So those actually are isomorphic. And perhaps more surprisingly, even these groups, because these groups aren't conjugates, there's no fiber-wise isomorphism from this guy to that guy. But on this one I do find more surprising, those groups are actually the same. In fact, in this case, you can convince yourself by staring at the mapping tori that the mapping torus of the top one actually is homeomorphic to the mapping torus of the bottom one. That this twisting of the pentagon goes away in the mapping torus if you refiber it. Okay, so all of those examples were not just to use up all the time, they were actually to convince you it's not obvious how you recognize that free-by-cyclic groups are isomorphic, which makes this theorem, well, perhaps it sheds a different light. Maybe it makes it better. It certainly sheds a different light on it, right? Because how are you going to prove it? You're not going to prove that the fiber is the same and then recognize whether the holonomy is the same. That can't work, right? Because you have all these different ways of fibering these free-by-cyclic groups. So let me tell you how you do it. Oh, incidentally, oh, sorry, I haven't got to that point yet. Did I just rub off Templeton? No, good. Are there any questions while I'm doing this?
I have a question.
Yeah?
So you've done all these crazy tricks for showing that these groups are either isomorphic or not.
Yeah.
Can you use your theorem to tell anything about them?
Yeah, right. That's a good question. See, so I think this is already known by different ways. But so then you start worrying, well, how hard is this problem, right, of recognizing isomorphism? But when you prove you've got profinite isomorphism in a class of residually finite groups, it automatically gives you a solution to the isomorphism problem. Because on the one hand, you can always, if isomorphism exists between finitely presented groups, you'll always find it by dumb luck, by just enumerating all possible maps back and forth. Right? So what you need is an invariant that says if they're not isomorphic, then I'll calculate this invariant if they're not isomorphic. And when you've got a profinite rigidity theorem, well, you just start listing the finite quotients of both groups, or you tell your computer to do it. And if they're not the same, then eventually you'll find one that's on the first list and not the second. So I wouldn't recommend it as a practical algorithm, right? But it is an algorithm for recognizing that these isomorphisms exist. Right. Right, so we need to change of perspective, right? And this is towards GBS, generalized complex Hilbert groups. So we've got to get away from being stuck with this fibering because we know it's misleading, right? So, so let me just try and draw an example. All right, so I'll take some isometry of that graph. Right? Oh, gee, that's a terrible picture. Okay. I take some isometry of that graph, I take the mapping torus. So instead of looking this way and taking the fiber and then the z acting, I'm going to look that way. Okay, I'm going to look that way. So it's got a natural, this is really an isometry, this graph, right? So it's got a natural, put some extra points in. It's got a natural cell structure. So I'll take a 0 cell here. So I'm supposed to take colors. Right, I'll take a 0 cell here, and I'll just follow it round. And I'll come back to some other 0 cell, and I'll just keep going. Right, and eventually it'll come back to itself. Okay? So the 0 cells in my fiber will give me circles. So 0 cells will give me circles. So 0 cells in the fiber will give me circles in the mapping torus. And if I take an edge, if I take an edge in the fiber, that will give me an annulus in the mapping torus in the same way. Yeah. Now they don't just go around once, they'll wrap around a few times before they close up. Right, but I'm just going to take that structure. Right? So this mapping torus is naturally, I say by just looking the other way, the mapping torus is naturally a graph in the sense of Scott and Wall, it's a graph of circles. Right? So it's like a graph of groups, you know, you just say where all the spaces are. They're all circles, and they're attached by some maps, covering maps. Okay. So actually, what you get, you just get some graph, and it's a graph of spaces. And if you apply pi1 to it, the functor, think of pi1 as a functor. You probably have to think of groupoids. That's a graph of groups. That's a graph of groups decomposition of our group as a graph of sets, right? Just as a graph of infinite cyclic groups. Okay, and that's a generalized Baum-Cyctolog group. Now it's a generalized Baum-Cyctolog group of a particular type. Okay, so we're getting our group gamma, our free-by-cyclic group, is now the fundamental group of a graph of a finite graph of sets. But it's not an arbitrary one, because there's a preferred orientation, right? I can go around in the holonomy direction. So all the local groups, so all the local groups in this graph of groups have a preferred orientation, or if you like, a preferred generator. So all you need to know is, so you got some graph of groups, you got a Z everywhere, you got a Z on the edges, you got a Z, Z's and Z's are coming and going. They're isomorphic, don't worry about it. You got Z's everywhere, and all you need to know, because you have a preferred generator, you have at the end of each edge, say this is edge E, you have an integer at the plus end, and you have an integer at the minus end, that just say what the index of the edge group is in the vertex group. And they're all positive integers. That's important. They're all positive integers. And another key property is the so-called modular homomorphism. If you look at the map to Q star that comes by multiplying as you go around loops, that will be trivial. If you go, there'll be no holonomies. You go around this graph of groups and multiply all the indices, taking the ratio as you go through a vertex, that'll always give 1 when you go around a closed loop. Okay, now I said that very quickly. So just think that the graphs of Z's, or Z's, with special properties, right? Preferred local generators. Oh God, yes. Okay, so in the remaining 2 minutes, oh God, I'm not going to get to tell you the proof. I really like the proof. Right, you start working with these graphs of these. Now, just as the fibrings aren't unique, these aren't unique decompositions, but those who've worked with these things called spaces of group actions on trees, you'll know there'll be slide moves here. Sliding moves where you slide the graphs around will account for all isomorphisms. What you reduce from this graph of Z's, you factor out the center. The center isn't quite what you think. These examples are supposed to show you the center isn't quite what you think. You factor out the center of this group, you'll get a graph of finite cyclic groups. And the harder theorem that we prove is that free by finite cyclic groups are all profinitely rigid. So we factor out the center of our groups. We then prove this theorem. That theorem is proved by you. This is where some of the theory of profinite groups comes in, including a bit of profinite Basset theory. What you do is you have to understand the centralizers of finite cyclic groups in the profinite completion, and then decode that back into the discrete groups, and then have a way of going from this back by lifting slide moves back to the center. So I was going to explain all that to you. But that's the plan. The key idea is to switch from the fibered direction to the generalized bound-like solid type version. This is really the hard technical theorem. Free by finite cyclic groups are profinite rigid. These are not semi-direct products in general. Okay, they don't split these extensions. But let me come back, because I promised I would, in the remaining minus 11 seconds to deficiency. Okay, so sadly I'm not going to get to sketch anymore of that. It's a shame, it's a nice proof, but that's the theorem. I've got to tell you the theorem. Okay? Right, now, Rich asked a good question, which is, can this theorem be used to tell that things are different? Yes, it can. Okay, so let's take these two groups over here. We didn't resolve whether these two groups are the same. If they're the same, then they should have the same profinite completion, of course, and vice versa. So let's count subgroups of index 6. This one has 175. This one has 131. Right? So those groups are not isomorphic. Okay? Now, you might guess that. Now, but they're non-isomorphic in a very interesting way. They're both two generator groups. But the first one, let's get more. Let's go to, for gamma 1, hang on, I better get this the right way around, is a one-related group. It's not an obvious relation. I think that's length 54 of the relation. Okay? It's a two-generator, one-related group. Gamma 2 is not a one-related group. Which means the deficiency, well, it's a free-by-cyclic group, so the deficiency is, I gotta get my sign right. One, thank you. Thank you. The deficiency is 1. The deficiency is 1 because it's free-by-cyclic, but it does not have, in fact, it's a two-generator group, but it's not a one-related group. Doesn't have a two-generator, one-related presentation. And therefore, you cannot.
How do you know?
Right. How do you know? That's hard, right? So I sweat my guts out to prove this. It turns out, so this is implicit in the literature. So first of all, it's not just, you have to consider all possible systems of two generators for this group. And then you can do that, because it's free by cyclic, there's some machinery that was developed by Zishang and refined by Collins, where you can figure out what all of the two-element generating sets are. And then there's a bunch of work under the heading of one-related groups with center by people like Piotrowski and Collins. And then the key paper is by Jim McCool, in which he gives a criterion for recognizing whether a certain type of two-generator group is or is not a one-related group. And this, you can adapt this. This is more or less on his list And so you can see that it's not a one-related group from his criteria. So that's what I mean to say, I was very pleased to prove this. That's what I meant when I said it's been implicit in the literature for a long time. That this particular group, for example, if you read the papers of Piotrowski and Collins and McCool, you could see that this is a two-gender group that's not one-related, but it is free-by-cyclic. Okay, I'll stop there. Thank you.
Well, we have only minus 3 minutes left, so maybe some quick questions.
No, that was for 10 minutes of questions. We have 6 minutes.
4 minutes.
Okay.
But
Yeah, I'm not sure I really understand. So for the last example, you said that gamma 2 is not a one-related group. Ah, okay, but the deficiency is still 1. Okay, no, so still I have a question about the deficiency. So are there some invariants or things that you can use to...
Well, it's very hard, right? This is why it's such a hard problem, deficiency. So why this works is this literature I was talking about one-related groups with center. In a very specific class of groups, you can work with them and think about all possibilities for generating sets from relators. So there isn't really an invariant there, right? So there's a theorem that gives a criterion, but it's really by understanding all generating pairs and thinking about all one-related presentations. So it sort of gets around the problem of there being no invariance. And what makes deficiency hard in general is that all of the invariants we know for getting lower bounds in the number of relations you need are homological. And that's just not good enough, right? So in general, you don't have invariance, but in this very specific class of one-related groups with center, you can just work in that class and get criteria. And this paper of McCool, which isn't well cited, has the key ideas in it.
Did you give an answer to this old problem about deficiency?
Yeah, but I'm sort of slightly embarrassed by it because the answer is really, well, if you read this paper, and this paper, then there's an example. So, yes. So yes, I gave an answer, but the answer was, in the end, it was already in the literature, I think, is the honest answer. Yeah.
So I have just a quick question about this finite genus theorem that you mentioned. So given a hyperbolic 3-manifold group, is it computable how many finite quotients it has? So can you recognize that?
It probably is computable, actually, in principle, but you have to pass to a fibered cover. Okay. Well, we don't have good estimates on how deep that is, but since you know it exists, you could just dumbly search for it. And then you can work out what the holonomy is. Then you've got this fake guy who will have a cover of the same index. And then you know how many mapping classes, you can compute how many mapping classes have the same dilatation. So that's some family. And then the number of possible finite extensions is another finite family you can compute. So I guess in principle it's computable, but not in a very practical way.
But that gives a solution to this isomorphism problem in that class too.
Yeah, it does. Yeah, and you already know a solution to the isomorphism problem because you know the Borel conjecture in dimension 3, and Zeller's solution to the isomorphism problem for hyperbolic groups will do it. Now, Henry's...
It's easier than that.
Yeah, you told me this before, but I like what I just said.
The paper stuff and show me directly.
Oh, yeah, thank you. Yeah.
I need some.
Do you have profinite rigidity for like cat 0 generalized bumps of solid groups?
No. There's the free-by-cyclic nature of these things. I say you throw away the free-by-cyclic nature, but the fact that they have a center is really important. So when it really comes down to these free-by-finite cyclic groups and understanding them, so it doesn't generalize to that. This proof doesn't generalize to that.
okay, thank you very much for